This question asks us to find the sum of four vectors, and it's interesting because two of the vectors, vectors A and C, are written in unit vector form, and then vectors B and D are written in a different form. I suppose we could call this magnitude angle form. And it's going to be helpful if we first convert vectors B and D into a unit vector form. And to do that, we will proceed as follows. Let's say that we wanted to find the x component of vector B. Then all we need to do is take the magnitude of vector B, which is given, and then multiply that by the cosine of the given angle. So for example, vector B has a magnitude of 4 meters, and then we'll multiply that by the cosine of the given angle. Now when you do this, just make sure that your calculator is set to degree mode. So let's go ahead and calculate this. And we end up getting the x component for vector B as approximately 1.69 meters. Now we're going to also want to get the y component for vector B, and when you calculate the y component of a vector, you take the magnitude of that vector and then multiply by the sine of the given angle. So in this case, we'll take that 4 meters and then we'll multiply it by the sine of 65 degrees. And we end up with a y component of approximately 3.63 meters. So you're going to want to do the same thing for vector D. It's got a negative angle, but that's fine. You still want to proceed in a similar fashion. So go ahead and do that, and for vector D, you should get the following x and y components. For the x, you should get approximately negative 2.87 meters. And then for the y component, you should get approximately 4.10 meters. So now that we've found those components, we can write vectors B and D in this so-called unit vector form. So for example, for vector B, looking at the x and y components, we have 1.69 and 3.63. You would write that as follows. You would simply write 1.69 meters, and because it's an x component, we use the I hat notation for that vector, for that component of the vector, and then we add the y component, which is the 3.63 meters, and because that's the y component, we use a j hat notation. Proceeding similarly for vector D, we would have the negative 2.87 meters I hat, and then plus the 4.10 meters j hat. So now that we have vectors B and D written in that unit vector form, and we also have vectors A and C in the same form, we're going to organize those vectors into a table that will illustrate their x and y components respectively. So let's go ahead and do that. So now that we have organized the vectors into this table, we have the x components listed and then the y components listed, we can very easily find the sum of these four vectors. We're just going to call that sum R, which stands for resultant. And it's quite simple. For the x components, all you're going to do is just add them together. So when you add those components together, you will get approximately negative 3.18 meters. And then when you add the y components together, you will get approximately 4.73 meters. Now, we go back to the question and just remind ourselves that in part A, we need the sum of the vectors in unit vector form. So we can do that now. We can say that the resultant vector will have a negative 3.18 meters. That's the x component. So once again, we use I hat notation. And then we add the y component, which is 4.73 meters, and we use j hat notation for that y component. And that's it. The answer to part A would be those two components added together. That's unit vector form. In part B, we are asked for the magnitude of these, or of the resultant vector, excuse me. So to find the magnitude, it would be useful if we constructed a diagram that illustrates these x and y components of the resultant vector. So again, the x component is negative 3.18 meters. Notice that because it's negative, when you go to draw this, you want to point on the negative x-axis. Now, we probably can't see that very well, so let's just thicken up the font a little bit. We'll do that again. So we're going to draw that x component like that, and again, it's pointing on the negative x-axis. And the magnitude, or the length, if you will, of that vector is the 3.18 meters. I generally leave off the negative sign when I draw these diagrams, and the reason for that is because the arrow, or the vector, is already pointing in the negative x direction. So it's a bit redundant if you were to label that negative 3.18 meters. The leftward pointing arrow already shows that it's negative. Now for the y component, it's positive 4.73. And because it's positive, we're going to point that magnitude, or that vector, in the positive y direction. So it's going to go this way. It's going to go straight up. And we're going to label that with the magnitude of 4.73 meters. Now, the actual resultant magnitude that we're looking for would be this vector right here. We have sort of switched the colors a little bit. That's okay. We can still label this the resultant. And you might want to ask yourself, how would you find that resultant? You're trying to find the length of that vector. Now, of course, we have drawn ourselves a right triangle, so we could simply apply the Pythagorean theorem, and that's what we will do. We will take one leg of the triangle, 3.18, we'll square it, and then we'll add the square of the other length, and then we'll set that equal to the square of the hypotenuse. Now, we'll go ahead and simplify the left-hand side. And that will be approximately 32.49. This is going to equal the magnitude of the resultant squared. So then, of course, we just have to square root both sides, and we get a magnitude of about 5.7 meters. That would be the answer to part B. That is the magnitude of the resultant. It's 5.7 meters. In part C, we need an angle. So let's go back to the diagram. And the angle is a bit ambiguously asked for here. They're not specifying from what axis we want to measure this angle. So we'll come up with our own solution to that. But first, we actually want to find this angle inside the triangle. You always want to find that angle. The one that's touching the x-axis is usually the right angle to find. You don't want to actually find this angle up here because it's not touching the x-axis. And again, we usually measure our angles in relation to the x-axis as opposed to any other axis. So we're looking for that angle theta. We can use some trigonometry. If we study that triangle carefully, we can see that the 4.73 meters is opposite of the angle that we've marked. And then we can see that the 3.18 meters is adjacent to the angle that we've marked. And of course, a trigonometric function that involves opposite and adjacent is the tangent function. So we know from trig that the tangent of our angle is going to equal the opposite over the adjacent. And again, the opposite is 4.73 meters divided by the adjacent 3.18 meters. Now, to actually find the angle, we have to use the inverse tangent function. So just be cautious here. The angle actually needs to be the inverse tangent of this ratio that we have already written down, the 4.73 over 3.18. So we'll grab our calculators, staying on degree mode, and when we take the inverse tangent of this ratio, we're going to get about 56.1 degrees. So that's the angle that's inside that triangle. Now, your homework system or your professor might want you to actually find this angle. Maybe we'll just kind of call that theta prime to distinguish it from the blue angle that we've already marked theta. That's pretty common. Usually angles are measured from the positive x-axis. So from this axis right here. So we would need that angle. And if you study the picture carefully, you may come to realize that the angle in blue added to the angle prime, that green angle, they form a straight line altogether. So that would have to equal 180 degrees. And thus, the angle that we are looking for, that green theta prime, is going to equal 180 degrees minus theta, minus the theta that we had found. So that's what we're going to do. We're basically going to take our 56-degree angle and subtract it from 180, and that would give us our answer. So theta prime would actually be 180 minus the 56.1 degrees, and in that case, we get about 124 degrees if we kind of round to 3 digits. So theta prime is equal to 124 degrees, and that again is relative to the positive x-axis. So we might just want to make a note of that, relative to the positive x direction. That would conclude the answer to part C.